Welcome back everyone, and in this video we are quickly going to discuss another very interesting architecture which can be used for constructing layers in neural networks. We're talking about convolutional layers or convolutional neural networks, and it's a very popular architecture, especially well known for its applications to the processing of, for instance, image data, such things as face recognition and techniques similar to that are based on the application of convolutional neural networks. To be fully honest, so far I haven't seen many good applications of convolutional neural networks to the area of finance or to financial data. That's why we are not really putting a big emphasis on convolutional networks. But the idea behind them and how they work, I think, is so interesting that we really should not skip that in that course, okay? So in the last videos, we talked about recurrent neural networks, which I consider to be kind of natural for the application to financial data, because in finance we often have time series of data, yeah? And so convolutional networks are also some kind of filtering mechanism, not in the same way as we have seen it for recurrent neural networks, which I would consider to be a sort of filtering mechanism which, it proceeds information over time. There are many different explanations, especially once you start in understanding the idea of convolutions. And what helped me in the end the most in understanding it is, regarding convolutions as a filtering mechanism. Usually it is applied in like 2 or 3 dimensions, meaning when we have a black and white picture, that's like a 2-dimension, because we have the height and the width information of a picture and the pixels of the picture, and a certain number behind a pixel, which is indicating if this is rather a black or a white pixel. And that's how your picture of grayscaled images is generated by a computer. Or 3 dimensions, because obviously we are used to nowadays we are more used to colored pictures, which at least, for instance, need another dimension which generates the different color schemes in the picture, and that is often generated by using the red, blue and gray colors. So behind the the size defined by the height and the width of a picture, we also have the 3 different like a third dimension, usually also presented by 3 channels, which are combined in order to generate different colors for each pixel in a picture. Nevertheless, before we completely I'm completely drifting apart, what helped me the most is regarding convolutions as a filtering mechanism. And before we go into the filtering, how you can picture it for 2 dimension, let's just quickly take a look at how we would do it for 1 dimension. And this is also a possible application for you, because assume we have still a single, for instance, a single variable and its progression over time. Then we could also use a 1-dimensional convolutional filtering mechanism instead of, for instance, a recurrent mechanism. Both share some similarities, both are but also very different in certain ways. But that's here a simplified example how you can picture and what I mean with filtering. Because what makes is very characteristic for the convolution here is that we have like our the sequence of our feature variable. So that would be 1, 2, 3, and then we have a filter from which is used for the convolution. And here, if we have a 1-dimensional filter, means we have like only 1 dimension, like a vector, and those are the weights as you are used from the modeling of the networks. And now what we're doing is we go over the sequence. The sequence has a length 3 here with a 2-dimensional filter, and then we do element-wise multiplication and sum it up. So meaning in a first step we're going to filter the information of the first 2 elements in our original feature variable, and that is done by a element-wise multiplication and then the summing up of those values. So that means we go here and have 1 times the first value of the filter, that is 3, plus 2 times the second value of the filter, and that is 2. So we have 3 plus 4, which is 7. So the information that is kept in the first two values of our original sequence is now filtered to a single number, which is 7. And now we are hovering our filter over the whole sequence and do this step by step in a rolling window approach. That means, like, if we hover over to to the next step, then we have the values of 2 and 3 in our sequence, which are now condensed into one single number by using the filter again here. So 2 times 3 plus 3 times 2, which is 12, okay? And that is what I mean with filtering. So element-wise, depending on the size of your filter that you use here, we condense information of our original sequence. So here we condense the information always of two adjacent realizations here. So the first two, the first two realizations are condensed to a single number, and then the information of the second and the third observation are condensed into a single number using the same filter for over all the sub sequences of our whole sequence. Okay, and that idea can be further proceeded if we have more dimensions. So assuming we have 2 dimension now, that could be represented by a matrix, then that would be our original data here. And again, the filter size is something that we define. So for instance, here we have defined a 2-dimensional filter, and here we define we had defined a 1-dimensional filter of size 2. Here we have defined a 2-dimensional filter of size 3 times 3. And now what we're doing is basically again the same. So we would start here in the first in the corner, laying our filter over the first 3 elements regarding the 3 columns and 3 rows here, and then we conduct element-wise multiplication and sum up these values, and we do this step by step. So at a certain point we would reach that where we are here. So what we're doing now here is again element-wise multiplication. So 1 times 1, 0 times 0, 0 times 1, 1 times 0, 1 times 1, and so on. So I hope you get the idea, and I hope you can see it, because the what's multiplied with what here is also indicated by those light green numbers that are given here. This is just the values of the filter. If at a certain point in time we have our filter at this area of the original 2-dimensional input here. And if you can check that for yourself, for instance, if you do this at the first 3 rows and columns here, if you end up with the results that is here, and just check out for yourself if you would be able to calculate all those numbers here. And if you do that, then you understand how the filtering mechanisms work here, okay? And as always, for as you know it, for neural networks and so on, that's going to be not done only once. This is like how you could picture a single convolution, and a convolutional typically in a neural network is combined with multiple convolutions that are done sequentially, and this is also combined with other layer architectures, but we come to that in a second. But for a moment, without knowing anything about neural networks, you could picture convolution as a filtering mechanism, okay? So what results after the convolution is called the feature map, and obviously, like, this would be a single possibility of using, like, the values in the filter here are the weights, and obviously if you want to use more than one filtering mechanism, we can do that. We can define it by our own. That's like defining the number of neurons or hidden units in a layer. So if you want to make out of our original frame here, or the original matrix, if we want to make more than like one condensed version of the original data, then the only thing we need to do is use different filters, meaning filters with different weightings here. And as you may guess already, those are the numbers that are not given. Those will be the numbers that's going to be estimated and calibrated when we see training data. Now, what's different to a four neural network is that the neuron in the convolution layer, as you can see, read it here, it's not connected to each neuron in the previous layer, like for the fully connected layer or the dense layer, but only like to the neurons which correspond to a certain area. Okay, so like what the values that you can see here, they're completely independent of the values down below on the right corner and vice versa. And that's what's what's a big difference in comparison to a fully connected layer, or like the architecture of a fully connected network. If we do it like this, then we go like one step at a time, meaning the first number that we calculate here, we use the first 3 rows and the first 3 columns. The second number is the first 3 rows, but then the columns 2 to 4, okay? But we could, that's also not mandatory to do it in this way. What we also can do is, for instance, we can jump further each time we apply a filter. That means first we use the first 3 rows and columns, and then if we set the so-called stride, for instance, to 2, means we are not jumping a single step further, we're jumping 2 steps further. That means, for instance, we would then use the first 3 rows, but the columns 3 until 5, for instance, in the next step. So this is stride, and stride is something also that you can define when you define a convolutional neural network. Furthermore, as you can see here, as well as you can see here, if we do it in the way that we did it here, then by definition, the dimensionality of what results after we apply the filter is smaller than the original dimensionality. If for some reasons that's not a good thing and we need to retain the original dimensionality, that can be achieved by what is called zero padding, meaning we just to the left or to the right, or also to like if we have more than dimensions, we fill in the area around the original input with zeros in a way such that our output will have the same dimensionality as our input. Okay, I hope this just gets clear with the examples here. Okay, and if not, as I said, from my personal opinion, convolutions is for the moment like the last architecture which is really interesting to you, or really that is necessary for you to understand. Sometimes you can use convolutions like in analogy and instead to recurrent neural networks, and also we will play around with convolutions maybe when we are coming to the point when we are using also networks for the analysis of texture information. But if you think about the typical applications that we have in finance, to my experience, convolutions are the least applied architectures here. Okay, so I think you should heard about it, and I really love and like the idea of convolutions and convolutional networks, and especially also seeing their success when it comes to things such as image recognition or image classification. Nevertheless, if you feel that this is like a little bit too much for you right now, focus on the fully connected neural networks and the recurrent neural networks. Furthermore, what you also should hear about when you are becoming an expert with deep learning methods and neural network architectures is typically convolutions are combined with something that is called max pooling or some other pooling mechanism. But that I would say is strongly driven by the fact that usually convolutions are applied to images. And when you think about an image, then you know that, for instance, if you have a red car at some certain space in your image, the pixels in certain areas, they will be more or less the same, because in the whole range of the car there will be like strongly red pixels, and there is not much of a new information if you really like going through a picture in a very narrow sense. So that's why it's completely okay to further condense the information, and this is done by some pooling mechanisms. So assume that this whole matrix here is the output of a convolution. Then to further condense the information and to reduce computational intensivity, there is a, we have a max pooling mechanism also, which needs to be defined here is the size of the pooling mechanism. So again, in terms of a filter size, so if you use a 2 times 2 max pooling, that just means we use always the highest value of the 2 times 2 matrix over when we're hovering over the original matrix that you can see here. Okay, so I hope, again, as many times, this is way more complex when explaining it than directly seeing what it does in an example, and that's why I'm working with the examples here. So if we go over this whole input here, then we use, like we go later here and have like a 9, 2, 5, and 0 in that range. So we just use the 9 furthermore. Then also we apply this to the next block and to the next block. I mean, I'm not 100% sure, but obviously you could do it again with sequentially shifting this filter over. That kind of would not reduce dimensionality in the way it does here, but I guess like there are no specific laws how you need to do it. But as far as I'm aware, the common way to do the max pooling is to really shift that filter and not have any overlaps here. Okay. But I hope that gets clear. That with the example it gets clear what max pooling is. Okay. And then this is how you usually would see for a complete architecture of a convolutional neural network. Okay, so in the beginning we have an input. Assume if we have a grayscale image that it is a 2-dimensional input. I will show you also with an example in a second how that really looks like. And then we use different convolutional filters. Like each map here stands for the application of one specific filter to the original image. So here we have 1, 2, 3, 4, 5, 6 different filtering mechanisms which are all applied to the original image, which then leads to filtered information given by all these feature maps. And those feature maps are here have the same dimension, so that would mean that we use 0 padding here, but doesn't need to be, it's not really mandatory to do it like that. Okay. Then we have certain max pooling layer which further reduces the dimensionality of the feature maps. Then we use those feature maps and further condense that information again by using a additional convolution layer. It is quite common that the number of filters increases with the more we go forward in the network here. And at a certain point in time, what we are doing, if we only have very low dimensional or if the original information has been condensed to a rather low dimensionality in comparison to the original input image, then what's done is called flattening typically. That means if we have a 2 times 2 matrix here, then we just make out of the 4 values that are in it a vector of size 4. Okay, and then all those numbers are added. So for instance, if we have like 1, 2, 3, 4, 5, 6, 7, 8 filters here in the end, and we assume that each filter has 4 numbers in it, then after flattening all those values, then we have a single vector with 32 values in it. And those values are then preceded by a single fully connected layer, or could be also with like combining more fully connected layer after that. And then finally in the end we will generate an output. Usually when we are, for instance, in the area of image classification, then we will generate an output using the softmax function that has a probability prediction for each of the categories we want to classify our original images. To make this a little bit more clear, or to that you have a chance to at least grasp it and get your hands on it and get the idea and have the chance to see how that looks if we really work with real data. You can take a look at the Michelinis file in the collaboratory folder. I added this dummy example which is about identifying handwritten digits. Like this is the, I would say, most popular example once you're starting with neural networks. And it's the famous MNIST dataset, and which is you can collect with, for instance, Keras. You could also collect it with the sklearn package. And what the MNIST dataset is about, let's just Google it, and then you will find likely a high number of information and explanations. But yeah, for instance, here in Wikipedia and so on and so on, let me go to the English version. So it's a large database of handwritten digits that is commonly used for training various image processing systems. The database is widely used for training and testing in the field of machine learning. And what you see, I'm not sure if it's from a school or something, but it's a multitude of images where people have written handwritten digits, and that pictures have been scanned and are now available to us as users. And obviously those are pictures between 0 and 9. So we have a classification problem with 10 categories here, and that's what we're going to trying to do. So here we can, download the data, and let's just do that. Just need to wait for a second, and I think the download is also very quickly proceeding. What I'm already doing, or this is to be honest stolen from one of the Keras examples, but yeah, you will find many examples if you Google for that. So how does a single, picture look like? That's already rescaled. So let me just, take a look if I am quickly able to manage. Okay, sorry. So first of all, let's take a look at the shape of the data. So we have the batch size. So we have 60,000 pictures of handwritten digits in our training data set. Each image has is of size 28 times 28 when it comes to height and width of the image. And then we have the dimensionality of 1 here because we have grayscaled images. Okay, so for instance, taking a look at the first image, then you can see that there is, unfortunately, it's not easy to see that here. And like the original data would have looked like this. Okay, so everywhere we have a 0 here, that means it's white. And everywhere we have like numbers here, that indicates how dark the pixel is going to be. And that is how your computer visualizes pictures. And that is how we will be able to visualize the picture. In order that a network is able to better calculate those numbers and do optimization with it, that is why we typically scale this original data, which is between 0 and 255 for each value here, in the area range between 0 and 1, simply by dividing with 255. That's done here in the beginning. Okay, and that's why we have, like for a single picture, a shape of 28 times 28. And you can see here, so even though it's the other way around given here, we have the ability to show how images look like by using this pixel information. Okay, so obviously I just used the first 2 images in the data set here, and the first one seems to be a 5, and the second one seems to be a 0. So, but this is the visualization of the data I've been showing you here. Okay, so this data is visualized by the computer in that way, and the information that it needs for visualization is a certain are either zeros to show where we have nothing, and numbers to indicate the color intensity of the pixel that is given here. And now what is convolution? So we have a size of 28 times 28. A simple example of convolutional filters would be those that I'm visualizing here, meaning here we would have a horizontal filter, and here we have a vertical filter. And that is I do this here by hand, just to show you the effect of it. This is nothing that you need to do later, because the values in a filter is what will be learned by the network. But here you can see the numbers I'm using for the first filter. So those are 2 filters. So there are always 0, except for here in the middle we have 1s. And for the vertical filter we have always 0s, except in the middle where we have 1s. Okay? And if we apply those 2 filters to the input images, you can see what happens. You can see that what happens if we apply a vertical filter to the original image, and you can see, a horizontal. That's like the first 2 here. And this is how it looks like if we apply the vertical filter. You can also play around with a little bit by yourself. So for instance, let us increase the filter size here. And then we just need to make sure that it's still in the middle. So hopefully that will work. Okay, sorry, I need to also, and let's further delete this, that it's not getting messy. And so what's the problem here? Okay, that's the problem. Okay, now we should be good to go. So increasing the filter, yeah, let's just leave it as is. And applying this convolution, which can be done by a Tensorflow function. And if we increase the filter now, the more blurred it gets. And if we make it finer again, so if we reduce the filter size again to its original size that we had in the example, then you can now again compare one more time what happens. So that was like the bigger filter. And this is like if we make the filter finer. So I hope you see the effect here, okay? And I hope you can clearly identify that this is horizontal. Oh, sorry. I think I switched it up. This is vertical filtering. This is horizontal filtering, okay? I think I said it all the time wrongly before, but I think you get it, okay? And okay, but now let's get serious. Now let's define a convolutional neural network, and build it in a way that it is able to classify the numbers correctly. So it will learn that if a image looks like this, that this is a 5. If image looks like this, it is a 0. So as always, it is fortunately very easy for us, even for rookies and starters, to define a rather complex convolutional network structure in addition with a flattening layer and a densely connected layer. So because we can use the sequential API of Keras, as always, I am defining the input in the beginning. We could also use the input layer here, but it doesn't really matter. As I said, I copied that from the Keras side, so I'm doing it a little bit differently. But I also could use, for instance, here like layers and then the input layer, and then we would here like input shape. Okay, but let's not do this. Let's just leave it as it is. Here above the is defined the input shape, so that's how our convolutional neural network needs to know what the data is. So the size of the image, like height and width, and also the the third dimension would refer to the color scheme. And if we have colored images, then we, for instance, usually we have like here a value of 3. Because the information is not only provided by a single matrix with 28 times 28, it would be provided by, for instance, 3 matrices indicating the intensity of red, blue, and green, pixels. Okay, and in the way they are mixed, that makes up us all the other colors that you know. Okay, so once we've given the input shape, then we will use our 2-dimensional convolution here. And here we will use it, we do this 16 times, so we have 16 filters. So each image is processed in 16 different ways. Then we apply here the filter size, okay, that's how we do it. Also, I didn't set this before, but as always, of course, after we use the base filtering mechanism, which consists of element-wise multiplication and summation, we can use this number and put it into a activation function as we are used to it already from the other methods. That's not really something new or something spectacular. That's just how nonlinearity is always, or how how we allow our model to process information in nonlinear ways. Then we use a max pooling layer here with a max pooling filter size of 2 × 2, and furthermore, if it's not, I think by default the stride is set to 1 and there is no zero padding here, but that's all we could define differently when we are taking a look, for instance, at the TensorFlow documentation. I'm just showing you that here, that you know that you become familiar with how to best find out such things. So if we are here, then and always we're using the Keras API, go here to to the left to the Keras subfolder, or where all the information and the definition of the different objects with the Keras API related are explained, and then we go here to the layers. And here we'll find the convolutional 2D layer. And here you can find out that how the strides are set. Not sure, zero padding is not really specifically given here as far as I can see. So I guess we may need to define it in addition or on top of that. But let's not, dig deeper here because it otherwise may take too long. Ah, yeah, here we have the padding. Sorry. Okay, that's I was missing. So padding valid, but if we go below, then you can find same, and same is when padding same and strides, the output has the same size. So that is what I was referring to as zero padding, and so on and so on. Okay, so here you can find out many more things that you as a user could define, and also you can see the defaults, because the default is always how it is set and defined here. Okay, so as I said before, usually we are not using a single layer of convolution. This is typically combined with really multiple convolutions, and also the amount of filters used is typically increasing. So that's what I'm doing here, and so we have one more block of convolution and max pooling, and then after that, as explained before, I use a flattening, which just brings us a single vector of the processed feature information. In many times I use a dropout in order to prevent overfitting, but this is like something we need to find out later, maybe if that's a good idea or if it could be further improved if we do not do it, or if we change the dropout rate here, but by default I'm just using that. Okay, and then the only thing that always is mandatory is the output, and we need the output as it is needed for the classification task here. Here we have a multi-class classification task with 10 different classes that is also defined earlier here. So here we have set it to 10, and also if you take a look at it, how it is, for instance, for the first image where we have a 5, so that is 0, 1, 2, 3, 4, 5. So that is defined by one hot encoding vectors, the target, okay? And we need for each actualization a vector with 10 probabilities, each probability referring to the prediction that this observation is belonging to a specific category, and that's why we're using the softmax activation function here. As always, this can be helpful to check out the summary once we defined the model, and here that's I think really helpful and informative. Here you can see what happens with the dimensionality of the original input. So after the first convolution, the original 28 × 28 dimension has been reduced to 26 to 26. That is because we are using the 3 × 3 filter here. And as we wanted 16 filters, we have now 16 feature maps instead of the single feature map that we have in our original data. And then by max pooling, you can see that drastically the original dimensionality is further reduced. Then again, it is reduced after the second convolution, and this is further reduced after the max pooling. Then flattening, we have a 5 times 5 times 32, which should be equal to 100, I hope. And then we use a single densely connected layer, which generates out of 800 values for each image, 10 values, each value corresponding to a probability prediction, okay? Now, I'm not pressing play here because that takes like 5 minutes or something, but it has been pre-trained, and you can do that on your own, and you can play around with it a little bit. But you can see here that this is a fairly easy task, and it's the network here succeeds pretty early in the training process of almost getting all the pictures classified correctly, also for the validation and unseen data here. So in the end, we are, for validation and for training data, at an accuracy of about 98-99%, so pretty good, I would say. And basically that's it. Okay, we could stop here. Now we have the basics of convolution, but there's like one more thing which I really find always interesting and consider it to be kind of a highlight, because we can visualize, of course, what happens during convolution. So here we have how our computer sees the pictures in the beginning, and now we can take a look after the first convolution, for instance. So here for 16 times our original picture has been convolved with a certain filter, and now we can take a look how each filtered version of this image looks like for these 16 pictures, simply if we apply the operation of convolution and output those values in the same way as we output the original values when we are making them, when we make a picture out of those values, okay? And if we do that, so for instance, for the value of 0 here, so you could set that to 0, then you will see how it looks like for the 5. This is how the first filter sees now the 0. This is how the fourth filter sees now the 0. This is how the seventh filter sees how the 0 looks like. So you see that each filter is doing a little bit different things to the original image. And this is how convolution works. So we use the original image information, and by different filters, different aspects of a picture are highlighted. And then by focusing on different aspects, basically the condensed information in the original picture is refined and further processed. So this is, for instance, how it looks. The 0 looks like after the second convolution. Let me just take one more look here. Yeah, and I think that's pretty interesting, to be honest. So this is this is how before the, or is it before or after? Let me take a look. I did it even after the max pooling. So after the convolution, after the max pooling, for the first time, this is how the picture looks like, or how your computer or how your network will get the information that this is a 0, or how a 0 looks like. And this is after the second max pooling, how the 0 looks like, okay? And this information is then, flattened and further brought to a densely connected layer, which then generates the output. So obviously really something rather complex and I think fascinating. And especially fascinating because here we are really like, this is elementary school, okay? Like identifying digits. But these kind of architectures, they are really capable of identifying very specific things in pictures and classifying very accurate, very different aspects of pictures. Even though rather elementary school style, but still already astonishing are like data sets where our computer learns to distinguish between cats and dogs, for instance, or classifying different clothing and stuff like that. So really powerful. And last but not least, the information is also important to you, or important to know about when we talk about convolutions. Usually you are not starting on your own and defining a complete model. Nowadays, especially the highly performing convolutional architectures are already pre-trained models with not only 1 or 2 convolution filters, but with 10 or 15 different convolutional filters. And those are usually pre-trained on immense data sets of different images. And then if you have a new task, usually you will take the first layers of pre-trained models and the weights in them, and the weights are already frozen. And then you will put another layer on top and just, learn for a specific task the weights for the new layers, okay? But that does not need to make sense to you right now. And it is an immense amount of information, and it is, I would say, quite questionable for a lecturer to discuss this in a single video. But as I said before, the reason for us is, even though fascinating and I think pretty cool, I would say convolutional layers or neurons are what we as financial experts need the least. Of course, convolutions can be applied in analogy to recurrent neural networks, so it's still always a good idea to use, for instance, a one-dimensional convolution instead of a recurrent convolution and check out the performance of your model. So that's completely cool, but I'm just my personal experience, not really in most of the cases not really necessary to use convolutions. And yeah, it's like, I would say this is like what I think is most important to you right now. And as always, due to time restrictions, we leave it now with that information here and go further to the next topic, which I consider to be also highly applicable to financial data, and which is something new, because so far we talked about fully connected networks, recurrent neural network architectures, convolutional network architectures. Those are now, we discussed them in terms of prediction tasks. So usually we had in mind that there is going to be an output generated that relates to a certain desire to predict something. But now in the next video we're going to autoencoders, which also predict something, but where our interest lies in something else, and what we would refer to as unsupervised learning. And that is, for instance, in finding the basic systematic structure of multiple features and condensing information. And just be excited about that, because I think that is something that we really can use for financial data. And also I will provide you an example how we can use that. So stay tuned and check out then the next video where we start going to discuss autoencoders. For the moment, thank you for your attention, and as always, see you in the next video. Bye bye.